And that actually turns out to be the true gradient of the policy. And the policy gradient theorem tells us precisely what that means. That's just to formalize that, which is to say that if you start with some policy, then for any of those objective functions we considered earlier, the start state, the average reward, the average value, the policy gradient is basically given by this thing here, which is some expectation over the score function multiplied by the action value function, Q. So it basically tells you, again, how to adjust the policy so to get more or less of that particular action multiplied by how good that particular action was, or that particular action is in expectation. So you want to adjust the policy in the direction that does more of the good things and less of the bad things. And if you were just doing supervised learning and maximum likelihood learning, you'd have something which looked very, very similar, but you just wouldn't have this value function term here. You would just be adjusting things in the direction that made your policy achieve more of the things that your teacher tells you. And so what we have in reinforcement learning is instead of that, we adjust it for all actions. We just have to try those actions and see, well, are they good or bad according to our value function. Okay, so that's the policy gradient theorem. Let's consider the simplest way to actually use that now to make an algorithm. And we call this the Monte Carlo policy gradient, which is roughly the same as a really old, well-known algorithm called reinforce. And the idea is to update the parameters by stochastic gradient ascent. So we're going to get rid of that expectation now and just do something very practical. And we're going to use the policy gradient theorem. And what we're going to do is just sample that expectation. And the way we're going to sample that expectation is just to say what we wanted to... The term which appeared in the policy gradient theorem was this Q. So let's just sample Q. Let's just estimate Q by using the return as an unbiased sample of this Q. So we're going to be in a state. We're going to start by taking this action, and we're going to see what return we got, and we're going to use that as an estimate of Q. And we're just going to plug that in into our policy gradient to give us a direction, an estimate of the direction to move. And so every single episode now, what we're going to do is we're going to say, at each step, we're going to adjust our parameters a little bit in the direction of this score multiplied by the return that we actually got from that point onwards. And so what would that look like in an algorithm? Well, you'd start off, you'd pick some arbitrary parameters, you run your episode, and for that episode, so first of all you run forward, you generate all of your rewards. This is like a forward view algorithm, so you have to go all the way to the end of the episode, generate your rewards. At the end of that, you know what the return was from each of your steps now. So now you go over each of your steps again, and you say, for each of those steps, we want to adjust our parameters a little bit in the direction of this gradient, the stochastic gradient, which is the score, how to adjust our parameters in the direction that gets us more or less of something, multiplied by this sample return from that step. So that it's as simple as that. It's a very simple algorithm. So this is the most straightforward approach to policy gradient. You just sample returns and you adjust your policy in the direction that gets you more of those returns.
And GT in this case is R?
GT? GT is the sum of the rewards. It's the return. So it's the sum of the rewards from the beginning of the from time step T onwards until the end of the episode. So it's the same definition of return that we've used before. So GT is the return, accumulated rewards from that time step onwards. Okay, so here's a little example. This is using that same Monte Carlo policy gradient with a particular policy parameterization. And the idea is that you start off with this puck in this world, and this puck is sliding along. There's very low friction in this domain, and you just get to exert a small force on it every time step, which can just slightly perturb its direction. And so if you're not careful, it can really overshoot its target. And then the target is given by this pentagon, which moves around every now and then, and it has to try and reach that target. And so if it gets a reward when it gets close to the target, and it's reset every 30 seconds, and then you just go. You just run trajectories, and you use this Monte Carlo policy gradient, and you update in the direction of those returns. So you measure your return, you go back over it, and you adjust your policy a little bit in the direction that gets you more of those returns, and then you see how this works. And so there's two things I want you to take away from this. The first is that you get this very nice, smooth learning curve. Value-based reinforcement learning tends to be much more jaggy. You end up with sometimes collapses and sometimes chatters, but you can do very well. The second thing to take away, so it solves this problem very nicely, but the second thing to take away is that the scale here, that, I mean, we're talking, 100 million iterations here to solve this problem. So it's slow. Monte Carlo policy gradient methods tend to be slow. They're very high variance. They're looking at this complete return of what happened, estimating the gradient from that return and moving in the direction of that estimated gradient. And so the rest of this class is going to be about using similar ideas but making them more efficient. Right, how to take this very nice idea where you get this smooth learning where you adjust the parameters of your policy to solve a problem, but make it more efficient, reduce the variance, make it work better. Okay, and so that's going to bring us to the final family of algorithms, actor-critic methods. So just a quick recap. So the main idea is that we've got this high variance estimators of the gradient now. So we had this policy gradient. We plugged in the return to estimate the gradient by taking a sample of our Q values, but that thing's very high variance. Like, it might be that I'm playing, Atari again, and on one particular episode I might get a score of 1,000, and on the next episode I might get a score of 0, and that's just in the randomness of what happens, because, over the course of 10,000 steps there are many, many different random events which might occur. This thing's very noisy. And the main idea of actor-critic methods is that instead of using the return to estimate the action value function, we're going to explicitly estimate the action value function using a critic, using a value function approximator. We're going to bring back the ideas from the last lecture, combine value function approximation with our policy methods. So again, we're going to have our true action value function, and we're going to estimate this thing using a function approximator, and then we're going to plug this in to our policy gradient as a substitute for Q pi. So what this means is that we now have two sets of parameters, and that's why these are called actor-critic methods. We've got a critic and an actor. And so intuitively, the actor is the thing which is doing things in the world. It contains the policy, it's picking actions, it's actually making the decisions of what to do in the world. That's why it's called the actor. Whereas the critic doesn't actually take any decisions, it's just watching what the actor does and seeing whether that's good or bad, evaluating that thing, saying, oh, those decisions were good, they got a score of 1,000, or they got a score of minus 1,000. So we're going to combine those two things together, the actor and the critic, and the main idea is now to use an approximate policy gradient. Instead of the true policy gradient, we're going to adjust the actor, we're going to adjust the policy in the direction which, according to the critic, will get more reward. So the critic's going to say, hey, I think that if you go in this direction, you can actually do better. And then the actor's going to move in the direction of that gradient. And so the way we're going to do that, we're going to take our original policy gradient algorithm, which was an expectation of the score multiplied by the value function. That was our policy gradient theorem. But we've replaced the true action value function with this estimated approximate value function, where we've got our neural network or whatever to estimate this thing. And what we're going to do then is, at each step, we're just going to move a little bit, using stochastic gradient ascent. Every step we're going to move a little bit in the direction of the score multiplied by a sample from our own function approximator. So the critic is saying, hey, I think this thing is good, or I think this thing is bad, and then we move a little bit in the direction that gets more or less of the things that the critic says are good or bad. Okay? So how do we estimate the action value function? How do we estimate Q? What do we do for the critic? Well, that should be familiar. That's what we did last lecture. We started off with this problem of policy evaluation. We want to know, if I'm following some policy pi, if I'm following this policy pi, we're trying to estimate this Q pi. We're trying to say, how good is that policy? We're not trying to optimize it. We're not trying to build a critic that estimates Q star. We're just trying to say, according to this current behavior, how good is it? How much reward will I get under this current behavior? And then we're going to use that to point us in the direction that will improve our policy. So a way to understand this is we want to say, how good is this current policy pi u for our current parameters u? We want to know how good is that thing. And so we can use everything we've learned so far, Monte Carlo policy evaluation, temporal difference learning, TD lambda. Pick your favorite policy evaluation algorithm, least squares, temporal difference learning, anything you like. Throw it into the pot, get an estimate of your action value function, and use that to adjust your actor. So, here's a canonical example, just to make things concrete. So let's say we were using a linear value function approximator for our critic. So we're going to estimate Q by using some features of our state and action multiplied by some critic weights, V. So in this class, we're going to use V for the critic parameters, U for the actor parameters, just to keep those separate and distinct from what we did in the last lecture. So we're going to estimate our critic just by using a linear combination of features. And then the critic we could just update in the usual way using linear TD0. And the actor, we can update the actor parameters U by policy gradient, score multiplied by what the critic says. So that would look something like this. This is the Q actor critic. So basically what this is saying is that every step of the algorithm, now we don't need to wait until the end of the episode. This is now an online algorithm which we can, every single step, perform an update because we're using TD in our critic. We don't need to wait till the end like we do with Monte Carlo. So every step of our episode, or every step that the agent experiences, we're going to sample a transition. We're going to see what the reward was. We're going to see where we ended up after that step. We're going to pick an action according to our own policy. We're going to get the TD error between the value before that step and value after that step, just like we did in the previous lectures. Now we're going to update our critic in proportion. Our critic we can update a little bit in the direction of the TD error multiplied by the features. So that was linear TD0, so that's from last lecture. That's how to update our critic in a direction that minimizes the error between what we thought was happening before, what we thought the value was, and what the value ended up being after one step. This is like correcting our errors and making ourselves self-consistent. And we're also going to adjust the actor. We're going to adjust the actor in the direction that gets us more of the things that the critic says are good. So that's the actor-critic idea, using canonical case using linear TD. Okay, any questions so far? I'll just pause there before we're going to start adding more tricks to reduce variance, make these algorithms more efficient. So if you're feeling uncomfortable, now is the time to say, because we're just going to layer more pieces on from here on in. Yes, good.
Sorry. So you have a policy, you get a estimate, and then from that estimate you try to get another policy out. Is that true? That's
right, yeah. So we can think of this as another form of generalized policy iteration, where we start off with a policy, we evaluate that policy using the critic, and then instead of doing greedy policy improvement, we're moving a gradient step in some direction to get a better policy. So it's just like our familiar machinery, where we're making the policy better and better, and every step we're evaluating that policy, moving a little bit up the gradient to find a better policy.
My question is, choosing the first policy, does it differ?
Choosing the first policy, you can pick an arbitrary policy, so you initialize your policy parameters however you want. It could be, typically now we've just got parameters though, we're not using greedy anymore, we've just got some parameters, and those parameters determine our policy. I'm scaring people away from it. Okay, and we're making those policies, we're following the gradient so as to make those policy parameters better, so that our policy gets more and more reward out of the MDP. Okay, so we start off with some policy parameters, that determines our behavior. We want to make that behavior better and better and better. There's no greedy anymore, no epsilon greedy. The policy itself determines how we move around in this environment. These policy parameters, we're always picking actions according to the policy that's determined by these parameters U. So, yeah, one more question.
But if your policy was epsilon greedy over your Q function, do you fall back to Q learning?
Let me go back to a slide that I kind of skipped at the beginning because the projector was down. This one. Okay. We had this in the introduction, but I think it's worth reiterating. So let's classify our algorithms into either whether we have a value function that we represent, whether we have a policy that we represent, or whether we have both. That's what this Venn diagram represents. If we have a value function, if we represent that value function, we call it value-based. If we have a policy that we represent, we call it policy-based. And if we have both of these things in our algorithm, we'll call it an actor-critic. Okay? And epsilon greedy is something we do when we live in this side of the diagram. Epsilon greedy, we don't actually explicitly represent the policy. Instead, we use a simple trick, which is we say, if we've got the value function, if we've got q, we're just going to act greedily with respect to q, and sometimes act randomly. What we're considering now in this lecture is an alternative approach, which is to actually learn directly how to pick actions. We're going to parameterize the policy. So instead of doing greedy or epsilon greedy, we're directly parameterizing the policy. We're deciding how to pick those actions. And we want to figure out, well, if I pick my actions in a particular way, will I get more reward? Will I get less reward? And so we're actually in a different space here altogether, where we're directly parameterizing things. So there's no greedy, there's no epsilon greedy anymore.
But if you parameterize your policy to be like greedy over your q, over your value function.
If you parameterize it, so that's like an implicit parameterization, which I would say is what we call value-based here. So it's like if we're basically saying our policy is the thing which is acting greedily with respect to my value function, that's purely value-based.
Yeah.
We're not explicitly representing the policy.
But does that algorithm still work? With
Is there a way to recover
exactly.
like a pure value-based method?
Like Q-learning?
There's a result which says that basically, for a particular class of policy gradient algorithms that we'll see shortly, it turns out that if you take the limiting case where you make your step size bigger, so for all of these policy gradient algorithms, there's some step that you take in the direction of the gradient. And you could ask the question, what happens if you take an infinite step in the direction of that gradient? So if we just get back to where we are. So in all of these algorithms, there's some gradient update where we update our parameters a little bit in the direction of our score. And for a certain class of policy gradient algorithms, if you make this thing infinitely large, then it actually takes you to a greedy step. So that's true certainly for natural gradient algorithms, which we'll see later. So the step size is what kind of controls how greedy you are. So think about the softmax policy, okay, this thing where we were exponentiating some score. If you see that like one of these actions appears to be a little bit better than the other, so you had some policy where you were taking this left more often than right, and now you see something where left actually did even better than right, so you saw a good score for this guy. What are you going to do? Well, you're going to push yourself a little bit in the direction that makes left even more probable and right less probable. If you make your step size infinite, you'll push the probability of going right all the way down to 0 and the probability of going left all the way up to 1, which is equivalent to acting greedily. So there is a limiting case where you recover kind of greediness, and the step size is what controls the smoothness. So it's certainly true for some algorithms. Yeah, I'll take one more question and then move on.
Sorry, so when you were learning a value function,
Yeah.
you had the development operator being a contraction, and so you knew you were going to get to the optimal value.
Yeah.
Do you have the same thing here? Because you could have suboptimal sort of loads that you're...
Okay, this is a really great question. So the question was, if we're using policy gradient methods, do we still have the same guarantees that we'll find a unique global optimum, or could we get trapped in some local optimum? So it turns out that, at least in the case where we're using, so you could consider table lookup representations of policy. So let's consider the table lookup case. In the table lookup case, you can represent your value function by having one value for each state. And if you use the Bellman equation, you get a contraction, you guarantee that you get a global optimum. With policy-based methods, if you just follow the gradient, for example with a softmax, it's known that for the softmax that you also find the global optimum in the table lookup case. So if you have a softmax which is like a separate softmax parameters for each state, you also achieve a local optimum. Now, for the case where you've got some more general function approximator, it's clear that if you've got something like a neural net, neither method will guarantee that you find a global optimum. You can always get trapped in some kind of local optimum. For certain special cases in between, it's unclear, and I think it's an open research question, actually. Right. Okay. So we're still in this space where we've got like this basic principle. We've got this family of actor-critic methods. We've got this family where the actor is basically picking the actions. We've got some policy, we're using that to pick the actions. And we've got some critic, which is basically evaluating those things and saying, whether those actions are good or bad, and then actually the actor moves in the direction suggested by the critic. That's the basic idea of all of these. But what we want to do is to make these things better. So we're considering now some tricks to make this thing better. So the first trick, and perhaps the easiest and best known trick, is to reduce variance using what's called a baseline. So the idea is to subtract some baseline function from the policy gradient. And this can actually be done in a way that doesn't change the direction of ascent. In other words, it changes the variance of our estimator, we can reduce the variance of this thing without changing the expectation. So another way to say that is that what we're going to do is we're going to subtract off some term which looks like this from our policy gradient. So our policy gradient was the score multiplied by the value function. And we're going to subtract off that, we're going to subtract off the score multiplied by some baseline function. And now we're going to choose that baseline function just to reduce the variance, to kind of make this thing mean 0, to make it roughly about the right scale so that we basically, you don't want to end up in situations where one moment you see a reward of 1 million and the next moment you see a reward of 999,000, and you have to kind of adjust in the direction where you're always moving a policy's parameters up, but it's just the relative difference that determines how much up you should make them. It'd be much better to have like +1 or -1. And so this gives us a way to rescale things. And so very briefly, what we see is that if we just expand this out, so our expectation is just, this again is our expectation over states, multiplied by the gradient of our policy, multiplied by the baseline. We can pull the baseline outside of this sum because it doesn't depend on the action. We can pull the gradient outside of this sum. And then we know that our policy sums up to 1. This is a probability distribution, so the probability distribution must sum to 1. So now we have the gradient of 1. Gradient of a constant is always 0. And so we see that this whole term here is actually 0. Right? This whole term that we're adding or subtracting is 0 mean. It's got 0 expectation. Okay? So it's completely legitimate to add or subtract any term of this form. So what that means is that we can basically, whenever we have our value function, so if I go back, whenever we had our value function here, this was our policy gradient theorem, and our policy gradient theorem told us that the direction we really want to move is this score function multiplied by q. But now what this result tells us is that we can add or subtract anything we want from this q. As long as that thing is just a function of state and not a function of action, we can add or subtract anything we want from this so as to control the variance of this whole term here. We want this expectation to be low variance, but we don't want to change the direction of ascent. And so we can do that, and there's a particularly nice choice that we can pick for this thing, which is going to have some nice consequences for us. And the particular baseline which we're going to choose is the state value function. Okay? So what we're going to do is we're going to start off with our q values, our action value function, and what we're going to do is subtract off the state value function. And what we're left with is something called the advantage function. This is something which tells us how much better than usual is it to take action A. So we're going to look at the q value of action A, which tells us how good is it to go left if I'm in a particular state, compared to how good is it to be in that state in general. And that tells us how much better than usual, how much more reward than usual will I get if I take a particular action. And so intuitively, that's just the right quantity to use in our update. So we call this thing D, like the difference, the advantage function. And so what we're going to do is now rewrite our policy gradient theorem in the following way. So this is still the policy gradient theorem. This is still just ground truth. We've just rewritten it by subtracting off a particular baseline function. And so our policy gradient theorem we can rewrite as the expectation of the score multiplied by the advantage function. So again, let's see if we can understand this intuitively. It's basically telling us, this tells us how much better than usual is a particular action A. And this tells us how to adjust our policy so as to achieve that action A. So if this thing is ever positive, if we ever do better than usual using a particular action A, this will tell us how to move in the direction that achieves that gain. If this thing is ever negative, this will move us in the opposite direction, away from the direction that achieves that particular action. So this is always pushing the policy parameters towards situations where you do better than usual. Okay, so that's the advantage function. So again, we're just rewriting the same policy gradient theorem. So how do we estimate this advantage function now? How do we do this in our critic? Well, there's a lot of different ways to do this actually, and I'm just going to suggest a couple of them. So this slide is just to say, well, one way to do this would be to learn both Q and V. So our critic would basically learn Q. It could also learn V using yet another set of parameters. And we would just take the difference between those things as our estimate of the advantage function. So we could basically do that. This becomes more complex in the sense we have more parameters, but it gives us a literal estimate of the advantage function, which we would then plug back in here. So we can plug into this policy gradient theorem here. We plug into this advantage function the difference between our state action value function and our action value function. There's an easier way, and probably a better way, and that's what this second slide is about. So this is probably the most commonly used variant of the actor critic, although it depends who you talk to, and many people use many different variants. And it uses the following idea, which is that the TD error is a sample of the advantage function. So consider the following TD error, this d pi, this delta pi thing here. So if we knew the true value function v pi, then this basically tells us that the TD error is equal to the reward plus the discounted true value at the next state minus the true value in the state I'm in. That's just the definition of this TD error. Now, in expectation, we can take the expectation of this whole thing. We can say, well, what's the expected TD error? And the expected TD error is the expected reward plus discounted value at the next state minus the value of the state I was in. The expectation doesn't affect this thing because there's no random variable in here. S is what we're conditioning on. This term here, the expected reward plus state value at the next state, given S comma A, is precisely the definition of Q. This is just like unrolling our Bellman equation one half step. So Q is equal to the expected state value at the next step. And so this whole thing here basically tells us that the TD error is an unbiased sample. We've basically got our Q minus V now. This is the advantage function. This whole thing tells us that the TD error is an unbiased sample of the advantage function. So if we want to move in the direction of the advantage function, all we need to do is to measure the TD error and move a little bit in the direction of the TD error. In other words, if we ended up, I'm in a state where I think I'm winning a game, I make an action, I find myself in a situation where I'm losing the game, so that generates a TD error. These things were inconsistent. I now have to think, oh, well, I was probably losing the game all along. So you end up with this strong negative TD error that tells you need to reduce your value estimate. And so now what we're going to do is plug in that TD error as an estimate of the advantage to say that whatever I did on that step that generated that TD error, whatever move I made, it was probably a bad idea. So there was something which I was in a situation where I took an action that took me to a situation where I started off thinking I was winning, and I took some move and now discovered that I'm in a situation where I'm losing, so probably that was a bad move. And so that's the intuition here. We're now going to plug in that TD error as an unbiased sample estimate of the advantage function. And the nice thing about this is that we only need to estimate V in our critic. We don't need to estimate Q, we just need to estimate the state value function. There's no actions that come into it. And what we do is we just plug in, so this would actually be another way to rewrite our policy gradient theorem. Again, this is just a rewriting of the policy gradient theorem. We haven't changed anything. There's no approximation yet. But if we use a critic to estimate V, if we use a V hat now instead of the true V pi, and we use the TD error based on our approximate TD, based on our approximate value function, and we just plug in that estimate of the TD error there, then we end up with something which is a good approximation to this policy gradient theorem. That's a practical algorithm. We estimate V, we generate TD errors using our V, and we move in the direction of those TD errors. And we only need one set of critic parameters V to do that. Okay. So just a couple more ideas to throw in for this family of different things that you can try, and then I'll summarize and just bring them all back together. I've got one slide at the end that hopefully is just like a summary where you can come back and say, these are the different things that you can do with ActorCritic. So this one is really just a reminder of the previous lectures, which is to say, what about this idea of eligibility traces and different timescales? So if you remember from the previous lectures, we've often reused this idea that you don't always want to go all the way to the end of the episode and estimate the return, and neither do you necessarily just want to take one step and bootstrap from the value function after one step, because that's biased. You often want to trade off the bias and variance between these two things using something like TD lambda. So now we're going to do the same thing with ActorCritic algorithms. It turns out that it's quite straightforward to do that. So if you remember from last lecture, we had a choice of things that we could plug in. So this is last lecture. You could plug in when you were updating your value function approximator. You could plug in the return. You could plug in your one-step TD target. You could plug in your lambda return. You can make any of these the target for your updates. And then we also had this idea of eligibility traces, which basically gave a backward view that was equivalent to plugging in this lambda return in the forward view. So hopefully this is starting to become a little bit familiar. If it's not, then go back to the notes, and because it's useful stuff, a key idea. So what we're going to do now is to plug in exactly the same idea to our actors. So first of all, we should say that you can do all this with the critic, and sorry, I think some of these should say V rather than W, but you can do all of this with the critic, where you can basically, as I mentioned before, the critic, we can evaluate our policy by any means we like. We can plug in any algorithm we want for our policy evaluator. It could be TD0, it could be Monte Carlo, it could be TD lambda, least squares, policy evaluation. Any of these are valid. And so we can introduce different timescales onto our critic by choosing a TD lambda or an eligibility trace. But that doesn't affect the actor yet. It doesn't affect the actor. And the question is, can we also get these different timescales on the actor? Can we get information to flow back more efficiently in the actor, so the actor's not just based on the current TD error, but based on something which bootstraps from all different time steps? And the answer is yes. And so, very briefly, all we're going to do is basically, we're going to plug in, so this is again our original, this is the true policy gradient theorem. The score multiplied by the value function, or the advantage function, equivalently. And what we're going to see is that there's different things which we can plug in so far. We've seen two different examples. We've seen that we can do the Monte Carlo policy gradient, which looks something like this, where we plugged in the return. So we used the return multiplied by the score as our estimate, and we subtract off some baseline here. So if we always just subtract off this baseline value function here, you end up with the return minus this value function multiplied by the score. When we used the TD error, we ended up with the one-step target, the TD target, the reward plus the discounted value at the next step, minus our baseline. Okay, so these are different targets. When we use the Monte Carlo target, we end up plugging in the return. When we use this TD error version, where we're estimating the advantage function using the TD error, we plug in the TD target and subtract off the value function as a baseline. So these are equivalent. These are different ways to estimate our original policy gradient theorem. These are different approximations. And sometimes it's a good idea to do this. This is a high variance, low bias estimator of the policy gradient. And sometimes it's a good idea to do this, where we introduce bias by bootstrapping from our value function, but we dramatically reduce the variance. And again, the goal is to get the best of both worlds, where we want to come up with a gradient estimate which bootstraps from our critic all kinds of different time steps. We don't just want to rely on our critic at this time step to estimate the gradient. We want to use the critic. So we want to be able to say, well, the critic at this time step says I should go this way. The critic at the next time step says I should go this way. So what we really want to do is to combine these together and actually move in some combined direction. And so that's the idea of using eligibility traces. And it's exactly analogous to the way we do it in value-based reinforcement learning, where we compute our TD error, we build up an eligibility trace, and the eligibility trace now basically is an eligibility over our scores. So we basically remember all of the scores that we've seen recently. And so if I had a high score for this particular action in this particular state, we remember that, we bump up our eligibility trace, and then later on when we come to make an update, we move in the direction where the scores have been largest most recently and most frequently. So the way to understand this is, the best way to understand this is by analogy with the eligibility traces in the value-based case, where you can literally look at the updates and you can see that wherever you had an eligibility trace in the value-based case, the updates were identical. Like if we were doing value-based reinforcement learning, we would look at, say, our lambda return minus our current value, and we'd have just multiplied directly by the gradient of that value function, not by the score. And so all we need to do is like a search replace. Wherever we had the gradient before, we search replace with the score, and that will actually work and give us a legitimate eligibility trace instead. Okay. So summary of this idea, so we're building up our toolkit of ideas that help us to make ActorCritic effective in practice. So now we've got a new piece to our toolkit, which is eligibility traces, how to make our actor make use of critics from many different steps all the way into the future. And the nice thing about this approach as well is that unlike Monte Carlo policy gradient, we can apply this online. We can basically use critics that build up things going far, far into the future, but we can do it online, and we can apply this in incomplete sequences or in situations where the environment is continuing, never stops, or in situations where we're working off policy. Okay. So I think what I'm going to do is I'll talk very briefly about this. So there's a really important question in ActorCritic algorithms, which is, in some sense, it should be the first question that you ask about ActorCritic algorithms, which is that we've used this critic, and we just kind of said, let's replace the true critic value with some approximation to that critic value. And we just plugged in that thing and hoped that the gradient that we follow is still correct. In other words, we started off by deriving the policy gradient theorem. We said this is the true gradient to follow if you really want to improve your policy. And then we substituted in something. We substituted in a critic, and we said, okay, well, you should follow what the critic says instead of the true value function. But how do we know that that's valid? How do we know that this really is pushing us in the correct gradient direction and we're not actually following some bogus gradient? And the answer is that, amazingly, if you choose the value function approximation carefully that you use, it's possible to pick a value function approximator that doesn't introduce any bias at all. In other words, despite the fact that we don't have the true value function and that we're approximating the value function, we can still follow the true gradient. We can be guaranteed to follow the true gradient with our policy updates. And that approach is called compatible function approximation. And compatible function approximation, I won't go into the details of it, but the main idea is to say that the features that we use to have a compatible function approximator, the features that we use are themselves the score function. We basically build up features for our critic where the features are the score of our policy. And if we use that particular type of feature and we use linear combination of those features, then we actually guarantee, according to the theory on this slide and the following slide, which I'll leave to look at afterwards, we can actually guarantee that we don't affect the policy direction, that we actually still follow the true gradient direction if we follow these compatible features. Okay. Now, I know that I'm throwing a lot of ideas at you, and there's a big soup of possible things to follow. I want to throw in one last idea. This is a recent idea. I think it's a useful idea to know about. And it's just this one slide, which is to say that so far we've considered these stochastic policies. We've considered these policies like a Gaussian policy, where we say, I want the mean of my policy to be this thing, and I'm sometimes going to take the actions which are like the mean, and sometimes I'm going to perturb it a little bit by some noise. But this thing can be very, very noisy. Like so far we've been estimating our policy gradients by sampling our own noise. We've basically got a noisy policy and we want to take an expectation over that noise. And it turns out that taking expectations of the gradient of our own noise can be a really bad idea. That this thing is really, really hard to estimate. And in fact, if you start off with like a Gaussian policy and you start to improve this thing over time, and you'd hope it would start to narrow down as you start to figure out how to solve the problem, that as this Gaussian becomes narrower and narrower and narrower, the variance of your estimates actually starts to blow up to infinity. Like it turns out that estimating the policy gradient becomes harder and harder and harder. The noise basically hurts you more and more and more as you get better and better and better at finding the right policy. And that's sort of an unfortunate property of the policy gradient algorithms we've seen so far. Turns out that there's an alternative, and this is something we did last year, which is to work directly with the limiting case. So instead of adding noise into our policy and then trying to narrow this noise down to something which is roughly deterministic, what if we just start off with deterministic policies? So we're going to start off with some deterministic policy, and we're going to adjust the parameters of this policy, this deterministic policy, so as to get us more objective. We're going to follow the same objective functions as we did before. And it turns out that if you just take the limiting case of the policy gradient theorem that we've seen so far, you end up with this very, very simple update, which has a slightly different form to what we've seen so far. But again, you should think of this as just another rewrite. This again is exactly equivalent. It's just the limiting case when we actually consider a deterministic function where we've narrowed our noise down to 0. Basically just got a deterministic function now. We're just picking the mean always. We're never adding any noise in. And it has this particularly nice form where we say all we need to do to follow the gradient to adjust the parameters of this policy, this should have a u there as well. If we just want to adjust the parameters of this policy to get more objective, all we need to do is to take the gradient of our own Q function. So we look at our critic. Our critic basically tells us, hey, look, you know, if you were, it gives us the gradient that says this is the way that will give you better actions. It says actually, look, this is how you, this only works for continuous action spaces, by the way, but it basically says here's the gradient of your value function with respect to your actions. This is how, if you were just to make this action here a little bit higher, you would get more reward. If you were to make this other action a little bit lower, you'd get less reward. So the critic already contains all that information about how to adjust the actions so as to get more or less reward. So that's all there in the gradient of Q. That tells you how to get more reward. Like just move left a little bit more, and you'll get a lot more reward. That's this gradient of Q. And then all you need to do is to work out how to adjust your parameters so as to get more of those actions which the critic is suggesting. And so that's the gradient of the policy here. So this is just the chain rule. It's the chain rule. It says adjust the policy in the direction that gets you more Q. And so that's the deterministic policy gradient theorem. It's very simple, intuitive, and in practice it seems to work a lot better than stochastic policy gradient in situations where we've got continuous action spaces. Scales up much better to high dimensions. Okay. I'm going to skip the natural actor-critic. So there's one more approach, which is in the notes, which is the natural actor-critic. The natural actor-critic is an alternative descent direction, or ascent direction, which has some nice properties. And it turns out it falls out very nicely in the actor-critic framework. That's there in the notes. Feel free to refer to it. But I wanted to put up this summary slide before we finish. And this is like a summary of all the different manipulations that we've done to our different actor-critic algorithms. So we started off with basically our policy gradient theorem. And what we did was we plugged in different approximations to this thing, where we said, okay, the gradient of our policy, we can get it by taking the score function and multiplying it by the return. We can multiply it by the value function. We can multiply it by the advantage function, so that should be a D. We can multiply it by the TD error. This was another way to estimate the advantage function. We take a sample of the advantage using the TD error. We can use an eligibility trace where we accumulate our scores. Instead of just using the current score, we accumulate an eligibility over all of our scores over many time steps. And we use that eligibility trace instead of just the one current score. And we can use the deterministic actor-critic, where we basically move in the direction that gets us more Q. Okay? All of these are essentially different variants of the same idea. They're all different ways. They're different manipulations of trying to say, move the policy in the direction that gets you more value. And then the way that we estimate value using the critic is what varies here. And the way that we make use of this, how we update our policy, is what varies between here and here and here. So the critic can vary, the actor can vary, but essentially they're all doing roughly the same thing. And for each of these cases, we can make a stochastic gradient ascent algorithm where essentially all we do is we just drop this expectation by sampling the thing which is inside. And in each case, you end up with a very, very straightforward, simple algorithm where all you do is you take a step, or an episode if you're doing the top one, and you look at what happened in that one step only. We now have the gradient of the score for that step. We took an action from some state. We know for that state how to have adjusted our policy so as to have taken that action more often. And we look at whether that step was good or bad according to our critic. If it's good, we push our policy parameters to do that thing more often. So all of these have very simple stochastic updates. And then the critic, we basically use our favorite algorithm, Monte Carlo, TD, TD lambda. It's the whole family of different approaches that we've considered before in previous lectures. Okay, that's it. Any last questions before we, in the last 30 seconds? Okay, thanks everyone. See you next week.